Good morning. Okay, let's quickly start with whatever we were discussing in the last class. Arshini, what were we doing in the last class? You remember?
Actually, I was not there in the last class.
Hello?
Hello, ma'am.
Yeah, Arshini,
Ma'am, actually, I was not there in the last class.
you were not there. Good. Nandana? Yeah, we were. Okay, Aman is absent even today. Vinay? Number 13, Vinay?
Ma'am, I was not there in last class.
Good. Anybody from roll number 1 to 20 who was present in the last class? 1 to 20? Ayush?
Yes, ma'am.
You were present?
Yes, ma'am. We were
Okay.
doing questions.
Okay. And what all things we have done while designing the belt drive? Have we calculated the diameters of both the pulleys?
Yes,
Yes
ma'am.
or no?
Yes.
Yes. Have we calculated the area of the belt, the cross section area of the belt?
Yes, ma'am.
Yes. What was the thickness and what was the width of the belt that we calculated?
Thickness 5.5,
Hmm.
breadth 64.54.
Okay. Okay, so we'll continue from there. We have calculated the area, but we haven't checked whether this belt is safe for initial tension or the initial stress. So we understand that for a belt, a tension del T, which is getting distributed on the tight side and slack side, and gradually the tight. Finally, it reaches to a stable or a static value of tight side, which is T1, and then a value of slack side tension, which is T2. So the same thing we are going to continue with. Somehow I didn't save the problem that we solved in the last class. So whatever we discussed in the last class, that part is missing. So if the initial tension is Ti, and then there is an addition of del T by 2 and del T by 2 on the either side of the belt, then the tight side tension T1 dash will gradually increase from initial tension Ti to del T by 2, and the slack side tension reduces from initial tension Ti minus del T by 2. And since we are representing torque also as T, to avoid the confusion for time being, let me use the forces or the tensions as F. Okay, so I am replacing this belt tension or initial tension with the term F, so that torque remains T. So I am rewriting the same expression. Let Fi be my initial tension, and so the tension on the tight side gradually increases. This is Fi plus del F by 2. And F2 dash, the slack side tension, this is Fi minus del F by 2. And F1 dash minus F2 dash, the difference in the belt tension, this is nothing but del F, which is continuously increasing as it gains the speed. And the torque T, since I am using term T for torque, so I replace a tension from T to F. This, as you know, is the difference between the belt tensions into the diameter radius of the pulley, which is this del F into D by 2. This is the torque. Now, as we have seen, this is a pulley, there is a belt around the pulley, which is continuously rotating in, say, whatever direction. There is an initial tension Ti on the either side. If this is rotating in the clockwise direction, this del T, the gradual increase in the tension because of stretching on one side and compression on the other side. So it is an extension on this side of the belt and the compression on the other side of the belt, that this tension changes minus del T by 2. So the extension on the tight side of the belt, if it is rotating like this is the tight side, this is the slack side. On the tight side, there is continuous extension of the belt, and on the slack side, the belt is getting squeezed or compressed. And the amount of extension on the tight side this is proportional to T1 minus Ti. Whatever is the final belt tension on the tight side minus the initial tension Ti, because it has increased from initial tension Ti gradually by an amount del T by 2 to an ultimate value of Ti. So the total extension is proportional to T1 minus Ti, or I can write down this is some constant K into T1 minus Ti. Similarly, the compression of the belt on the slack side, this is proportional to the initial tension Ti minus the final tension T2, which is the tension on the slack side, or some constant K minus Ti minus T2. Now, assuming that creep phenomena is very, very slow and it takes a lot of time, so while we initially start the design, we neglect creep initially, and so the length of the belt is constant. For the length of the belt to remain constant, it is continuously extending. Extension should be equal to compression. And this value of K, T1 minus Ti, this is equal to the value of K, Ti minus T2. And the constant of proportionality is same because extension and compression are directly proportional to this ratio of difference. And if I cancel out this, I get 2 times of Ti is equal to T1 plus T2, or the, I have again gone back to T. Or if I take the initial tension as Fi and the tight side tension as F1, slack side tension as F2, this is F1 plus F2 by 2. This is more for understanding how initial tension depends upon its average of the tight side tension and the slack side tension, and this initial tension is less than the tight side tension and it is more than the slack side tension. So in few books you would get this relationship of initial tension as F1 plus F2 by 2, and in other books you would get this extension is proportional to root over T1 minus root over Ti. And on calculation will not make much of a difference, but then as I said, few books are giving this relationship. Under root of initial tension is equal to average of square root of these two tensions, F1 plus F2 by 2. So this B.D. Shivalkar design data book that we are referring is also using this equation for initial tension. So as I said, magnitude wise, this will make a little difference, not much of a difference, but different books of machine design would be using different expression. So I repeat, extension is proportional to difference between the tensions or difference between the square root of their tensions. Similarly, the extension is proportional to summation of tight side and initial tension, or proportional to difference between the square root of tight side and the initial tension. So we are going to use this equation for our understanding. But as I said, this equation is also used. So we continue with the formula for torque, which happens to be F1 minus F2 by d by 2. This is the torque for the final tensions T1 and T2 or F1 and F2, where d is the diameter of the pulley. And so I am writing F1 minus F2 as 2 times the torque upon the diameter of the pulley. At the same time, F1 plus F2, as per equation number 1, this is also equal to 2 times the initial tension Fi. If these two equations, equation number 2 and equation number 3, if I divide this, what do I get? F1 minus F2 on F1 plus F2. This is equal to T by D into Fi. If I write down, or if I take over F2 constant, can I write this also as F1 by F2 minus 1 upon F1 by F2 plus 1, which is equal to T by D upon Fi. What is F1 by F2? What is the ratio of belt tensions, also written as yes, e raised to mu theta. So the same expression now I am writing as e raised to mu theta minus 1 upon e raised to mu theta plus 1 is equal to T by D upon Fi, where Fi is the initial tension, T is the torque, and D is the diameter of the pulley. Or this T by D is same thing, rearranging mu theta minus 1 on e raised to mu theta plus 1 into the initial tension Fi. And we have also seen that the tension F1 is initial tension plus the small change in the tension because of stretching and compression. And this del F we have seen above is also equal to T by D. This del F here we have seen that this difference in the belt tension, this is also equal to T by D. So from this expression, I am again moving del F by 2 is equal to T by D. So del F is T upon D by 2. So the del F by 2 is T by D. And T by D is this. So this is Fi plus Fi times e raised to mu theta minus 1 upon e raised to mu theta plus 1. This is the tension on the tight side. Or this is initial tension times. What would be this? 1 plus this upon this. What would be this? Yeah, quickly someone please. Sarvesh? Karthik? What would be F1 in terms of Fi? Sarvesh? This is 2 times e raised to mu theta upon e raised to mu theta plus 1. Correct. Similarly, can you tell me what is F2? F2 is Fi minus del F by 2. So if this is replaced by minus, what will be this term F2? So while I am adding this, plus 1 minus 1 gets cancelled. While I am subtracting e raised to mu theta, this term would get cancelled. And this will be t upon e raised to mu theta plus 1. So look at F1 and F2. They are a function of Fi multiplied by 2 times e raised to mu theta upon denominator, and this is 2 upon e raised to mu theta plus 1. And if I plot a graph for understanding, the effect of belt tension initial tension on the final tight side and slack side tension, if this is how the initial tension changes, and this is the belt tension. This is the initial tension. With the increase in Fi, if the value of F1 increases in this particular fashion, F2 increases in this particular fashion. And at any given instant, as you go on increasing Fi, the value of F1 would increase more and the increase in the F2 would be less. And ultimately you see that with increase in Fi, the increase in F1 is e raised to mu theta times increase in F2. And we know that e raised to mu theta, this is always a term greater than 1. You will normally get a value 2, 2.2, 2.3 or 3, 3.1 depending upon mu and theta. And so the increase in F1 is always greater than increase in F2. Or with the increase in belt tension, initial tension, F1 minus F2 also increases. So as you go on increasing the value of initial tension, the difference between F1 and F2, this increases. So this goes on increasing, and F1 minus F2, this is responsible for the power transmission capacity. So a higher belt tension will always give you a higher power transmission capacity, but then again you cannot increase the value of Fi to any given range because this F1 also has a limitation. Similarly, the higher value of Fi, this would induce a stress which is known as stress due to the initial tension. So this Fi would induce initial tension SI, which would be SI into the belt tension, where SI is the stress due to initial tension. Initial tension Ti or Fi. So the problem that we were solving in the other day, we got the value of area, and now we have to check whether that area is safe from initial tension point of view. So we'll quickly go back to that numerical which we were solving in the last class. So in the numerical of design a belt drive for the rated power of, what was the value? 10 kilowatt motor rotating at 1440 rpm, and the other pulley attached to the line shaft is rotating at 400 rpm. We are not going to solve this again. You have to quickly give me the values that we have selected. What was the design power for this rated power? (11 kilowatt). We use the service factor as 1.1. What was the material that we selected? Chrome, tanned leather belt. CTLB is the one that we selected. Then the joint, the belt joint that we selected. What joint we selected for the belt? Wire laced by machine, which gives an efficiency of 90%, giving the final strength of material as how much? 3.15 MPa. For this material of leather, what was the density given? 0.97. Everything is given in the design data book. Then we assume the peripheral velocity of the belt for a longer belt life, how much? 1000 meter per minute from the design data book. Since RPMs are known, peripheral velocity is known, so we got the diameter for the larger pulley and the smaller pulley, how much? Smaller pulley diameter 221, larger pulley diameter 7 796 without slip, and considering slip, this was without slip, considering 2% slip, we got this value as 780 mm. Then we calculated the center distance. Center distance we considered as 4 times d, I guess. 3120, 4 times of the larger pulley diameter. Then we assume the material for the pulley as cast iron. With coefficient of friction for this combination of leather belt and cast iron pulley as 0.35. Then we got the value of theta. How much? 2.96 radians. With mu and c known, we got the value of belt tensions T1 and T2. Now let me use T1 and T2 here, which was 1023 and 363. Good. We also calculated what is the space required, which is equal to the center distance plus the radius of the smaller pulley plus the radius of the larger pulley, which came out to be 3620 mm. This much space is required for this pulley. Next, we calculated the area. What was the area that we calculated? (355 square meters). So we got the value of area as the tight side tension upon the material of the belt minus rho v square, and we got this value as 355. Now we have had so many assumptions. The peripheral velocity was assumed, then the value of thickness 0.025 times d1, which came out to be how much? 5.5. And so the value of b, just a minute, hello. And the thickness came out to be 64. 64 mm. We got 60 or 64. Okay. And we also checked that this is within the range of permissible width less than B max. So this was okay as far as this was considered, but now we'll check for the belt tension. Refer design data book. We have to find out what is the induced stress allowable, and this is given on page number, what is the page number for belt drive? Page number 155, table 15.1. This is giving us the value of initial tension in terms of root over initial tension. Fi is given as tight side tension plus slack side tension. We are using F1, F2 alternately with T1, T2. Give me what is the initial tension. And from here, we have to also find out what is the stress due to initial tension, which will be initial tension upon the area. So is that coming out to be 25 Newton? Is that the value of Fi? F1 is 1023 and F2 is 362. Root of F1 plus root of F2 by 2. Yeah, it is 651. 651 Newton is correct. Area, you know, this is the tension. So what is the stress induced? Fi by A. Sarthak gave me the value of stress induced. 651 Newton upon 355 mm square, which gives you 1.83 MPa. Now refer the design data book, table 15.4. What is the value of stress due to initial tension given for what material we are referring? Leather. What is the value of SI given there? Hmm, 1.4 to 1.6, and our value is coming out to be 1.83. So the allowable value of SI for leather belt with initial tension is limited to 1.4 to 1.6. Our value of SI is greater, which means the belt would fail due to initial tension. So what do we do? To reduce this stress, we have to increase the area. We are not able to reduce the belt tension, initial tension, but we can increase the belt area so that the stress induced reduces. So what should be our new area? If we want the stress in this range, 1.4 to 1.6, the area should be this upon, let us take it 1.5. Let the stress be 1.5. What is the value of stress you have taken, Bharti, for area 434? Let us try to be somewhere in this limit. So let's take 1.5. So what should be the area? 1.5, okay. Is that 434? 435, okay. So we are increasing the area from 355 to 434 so that our stress induced lies in this range. And with this cross section area, we have to again find out what is T and D. If we are assuming initial stress is less than the ultimate strength, so why it should be in that range? Initial stress is induced, it's a component of stress which is responsible for the initial tension in the belt. And there are two criteria for design of a belt. Like for worm and worm wheel, we were designing it from heat generation point of view and strength point of view. Likewise, for a belt drive, we have to keep into mind these two criteria. One is the tensions T1 and T2, and then the stress induced due to this initial tension SI. So as T1 and T2, these are taking care of the material of the belt S0, and this is the strength of the belt, and this is the stress induced due to initial tension. So what we are trying to do is we are trying to make it safe from both the criteria. With the earlier value of this area, this was safe from its material ultimate strength point of view. So this value of T1, T2 and this area for the material of the belt, this was safe. Although this stress induced due to initial tension, this value is coming out to be much less than the material of the belt, but this might not withstand this amount of initial tension. So the efficiency of the belt goes down if the stress due to initial tension increases beyond this limit. And so the allowable value of stress due to initial tension has to be in this limit. So if this is satisfying this criteria it will definitely satisfy. For the same value of tension, if the area is increasing, the value of the actual stress induced would further go down. And so we are trying to check using both the conditions. Okay? Yeah. So the thickness is same, 5.5 that we have considered, say, B value will increase. So now B value is 434 upon T. Give me the value of B. $78.9. It is 79 now. We have to also find out what is the length of the belt. You know what is the formula for length of the belt? Was this expression for length of the belt derived in your theory of machines? In terms of center distance and diameters? 2 times the center distance plus pi d1 plus d2 by 2. Was this expression derived then? Yes or no? Pranay? Bharti? Yes. So this is not very complicated. It is just a sum of the center distance taken twice plus length of the belt, which is overlapping the smaller pulley and the larger pulley. So again, in terms of the angle of overlap, radius, and converting this angle of overlap again in terms of d1 and d2, you get this expression. Give me the length of the belt, d1, d2, and see everything is known. Derivation was not told. Please confirm, so we'll quickly go through this. Do you want me to quickly derive this? Okay. Let me take the figure from here. Allow me to take this figure. Okay, so a quick derivation, not more than 5 minutes. Please give me the values. Please draw this figure quickly. The law of overlap on the larger pulley would be greater. So let this, the point where it touches here is A, This point is B. This is C. Let it, the contact of the belt from the larger pulley be D, E. Let this point be F. Diameter of the driver pulley or the smaller pulley is D1, larger pulley is D2. The angle of overlap here, let this be theta 1, and the angle of overlap here, let this be theta 2. If I draw a line which starts from here and which is perpendicular to the line joining the center of the larger pulley to the point of contact of to the point of intersection or the point of commencement of the contact with the larger pulley, and if I take this angle as alpha, if this length is d1 and if this line and this line, although this is slack, but we normally for derivation purpose we are assuming it to be straight, this will form a rectangle. So if this diameter is d1, from here to here, this diameter is also d1, the diameter of the smaller pulley. And the length of the belt, this is equal to length of the arc ABC plus the length of the belt CD plus the length of the arc, which is the length of the belt here, DEF plus AF. Length of the arc, ABC length of the arc is equal to angle into the radius. So this will be D1 by 2 into theta 1 plus what would be this CD? If this center to center distance is C and if this angle is alpha, you will get this length as C cos alpha plus length of the another arc, this will be theta 2 into the radius of this larger pulley plus length of AF will be again same C cos alpha. And we also know that theta 1, this angle is equal to pi minus d2 minus d1 by 2 by C, not 2. And theta 2 is pi plus, which again comes from the same derivation or from the same figure. This angle is theta 1. This total angle is, if I draw a vertical line, this is 180. So this difference, this small difference, this is the difference between the larger diameter, the smaller diameter, that is this distance upon C, and this is taken as sine alpha. So for small angle sine alpha, alpha is taken as sine alpha. And so you get this term D minus D by C. And the value of cos alpha, what will be cos alpha in terms of D, D and C? Sine of alpha is equal to D2 minus D1 on 2, which is the radius, by C. For small value of alpha, sine alpha is equal to alpha, so we write down this as D2 minus D1 by 2C. This is how you get the value of alpha and you get the value of theta 1, theta 2. And cos alpha, right here itself, 1 minus 2 sine square alpha by 2, and sine square alpha by 2, since this is small, so we are taking this as alpha by 2 square, and value of alpha we are writing as d by d upon 4c whole square, and so this comes out to be, on simplification, d minus d whole square, d2 minus d1 whole square upon 8c square. Let me write down again, 1 minus d2 minus d1 whole square upon 8c square. And when you substitute this value of cos alpha here and theta in terms of d2 and d1, you will finally get the expression of length of the belt L. This part you can definitely do it yourself. D plus d by 2 plus 2c plus d minus d d2 plus d1, and this is d2 minus d1 on 4c whole square. So this is the expression that you get, and for the given length of the for the given belt design, quickly give me what is the length of the belt. Give me the length of the belt and then we'll stop. Seven, 8, 3, 7. Okay. It's almost 7.8 meters. Now this design is only for belt drive, but for the complete design, you have to design the pulley as well. In 2 minutes, let me take you to the table 15.7, pulley design. Quickly refer this table. We have already done the gear plank design, so this part you can do it on your own. You have to select the material which we have selected as cast iron. Now the construction, whether this is an armed pulley or it is a web construction or a solid construction, this depends upon what is the diameter. So our diameters are 220 and 780, which means it is definitely greater than 150. So we will be going for armed construction, which is pulley which will be having number of arms. Again, number of arms would depend upon what is the diameter. So you are normally in a solved problem or in a problem that you are solving or designing, you are expected to design only one pulley, either a smaller or the larger pulley. You can mention that you are designing the smaller pulley with diameter 220 mm. And for this diameter, for the width of the belt that we have taken, it is less than 300 mm width. You have to select the number of arms. The number of arm is 1. Number of arms are 4. Number of sets. What do you mean by number of sets? Somebody quickly. Number of set. This is your pulley. This is the rim of the pulley. You will have a shaft. You will have a hub. These are for the 4 arms. A number of set 1 is, and this is your rim and you have a shaft and you have only one set of arms. But if the width of the pulley is too large, if your pulley width is this large, then we have two set of arms. This is your shaft. Over this you will have a hub. This is one set and this is second set. This is the rim of the pulley. This is known as two sets. So you can see when the width is more than 300 mm, you have two set. Then you have to find out what is the moment on the each arm. You have to find out what is the hub diameter. The hub proportions are given based on the shaft diameter. And how do you calculate the shaft diameter again? Shaft diameter, like the one we calculated in the case of gear drive, will have the same way to calculate the shaft diameter here. Do you want me to take one problem on this pulley design? Else I was planning to go with the belt drive in the next class. Do you want me to design one pulley? Okay. Right. So next class we'll start with the pulley design for the same problem and then we'll go for the belt, V-belt. You see the syllabus is huge. It's so difficult to complete a problem in one hour class. That's the reason I am trying to engage all your Saturday lectures, which I know nobody is happy with that, but can't help. You have a lot of syllabus. Either I leave everything to you, give you as an assignment, design the pulley on your own, complete the V-belt drive on your own. I don't believe in this technique. So rather I'll take only Saturday's lectures, but I'll try to teach everything on my own. Okay, that's all from my end. Feel free to ask questions if any. Yeah, any questions, please? Any questions? Any doubts, Manas? Pranay? Okay. Thank you.